Hello, my darlings. So today we're going to talk about initial value problems. So we've already been looking at antiderivatives, and we're just going to expand a little bit more on that today. So we've been solving equations where we had something like dy dx equals 3x squared. That's what we call a differential equation. It's called that because we have the derivative dy dx. We know what the derivative is. That's a differential equation. We know that the antiderivative of dy dx is y. The antiderivative 3x squared is x cubed. And we know we always have a plus c to give us our general solution. Now, our general solution is really a family of curves because we have y equals x cubed, let's say, minus 2. We have y equals x cubed minus 1. We have y equals x cubed. We have y equals x cubed plus 1. We have y equals x cubed plus 2. And we could keep going in both directions for an infinite number of equations that would satisfy that differential equation. Up to now, the general solution has been perfect for us. That's all we've needed. But sometimes we need a specific solution. For instance, if we want to find the solution that passes through the point 1, 2, and this is called an initial value. It's a value that we know has to work. So let's take it as if we hadn't done it before. We take the dy dx is 3x squared. So we find our antiderivative, y. The antiderivative 3x squared is 3x. Add 1 to the exponent, divide by the new exponent, plus c. So there's y equals our x cubed plus c. That's how we got this general solution earlier. Now that we have that general solution, we're going to take this initial value, 1, 2, and we're going to substitute it into this general solution. Okay, now remember, the first number is an x value, the second number is a y value. So if we substitute, y is 2 equals x is 1, and we're going to cube it plus c. So 2 equals 1 plus c. That means that c has to equal 1. Now, this is not your answer. We have to put these both together to tell me that y equals x cubed plus 1. This is the particular solution to our problem. This is the particular because not only does this solution satisfy the differential equation, it is the only one that also passes through the point 1, 2. Okay, so that's how it works. Let's try just a couple more. So we are going to find the particular solution given the initial value for each differential equation. So our first differential equation, dy dx equals x squared plus 2x plus 3. So the antiderivative dy dx is y. The antiderivative of x squared is x to the third, divide by 3. Plus the antiderivative of 2x is 2x squared over 2. And yes, those 2's are going to cancel. So we're going to have x to the third over 3 plus an x squared. Now the antiderivative of the 3 here is plus 3x. We're not going to forget our constant. Now we have our general solution. But we're going to take our general solution and we're going to plug in these values. We know that when x is 2, y has to be 1. So we're going to substitute in here. The y is 1, the x is 2, and we have to cube that over 3, plus the x is 2, and we're going to square that, plus 3 times the x is 2, plus our constant c. All right, now we have 1 equals 2 cubed is 8 over 3, 2 squared is 4, plus 3 times 2 is 6, plus c. So now we have 1 equals 8 thirds plus 10 plus c. We can subtract that 10 and we'll have negative 9 equals 8 thirds plus c, right? Now we're going to need, in order to solve for c, we're going to need to subtract that 8/3 from both sides, right? But if I want to be able to combine that with a -9, I need to write -9 with a denominator of 3. So that would be -27, which means that our c is -35/3. Now remember, we're not done. We need to take this general solution with this c value, put them together, and we have y equals x to the 3rd over 3 plus x squared plus 3x minus 35/3. This is our particular solution. One more. See, we're getting off easy today, only 3 problems. Now this one, our differential equation dy dx is x squared plus the square root of x. Before you try to take the antiderivative, you're going to rewrite this as x squared plus x to what exponent? What tells you to take the square root? An exponent of 1/2. Now we're ready for the antiderivative. What has a derivative of dy dx? That's y. What has a derivative of x squared? We add 1 to the exponent, divide by the new exponent, plus x. Now this 1/2, we have to add 1, so 1 plus 2 is 3 over the denominator 2. We need to divide by that exponent 3/2, but that's the same as multiplying by the reciprocal 2/3. Don't forget the plus c at the end. All right. We also know that we want the particular solution that passes through the point 1, 1. So when we substitute that into our general antiderivative, we're going to have y is 1 equals x is 1 cubed over 3 plus 2/3 times 1 to the 3/2 plus c. So that's 1 equals 1 to the 3rd is 1 over 3 plus 2/3. Now 1 to the 3/2 is just 1, so we're good there. Plus c. But what's 1/3 plus 2/3? That's 3/3 or 1. So that means that our c is 0. So if our c is 0, that means that our particular solution is y equals x to the 3rd over 3 plus 2/3 x to the 3/2. And we don't add a constant. There we go. Good job, guys. So remember, initial value problems, we start off exactly the same as we do for an antiderivative. We find the general solution to the differential equation, but then we take the point that we were given in the original problem that we know the particular solution has to pass through. We substitute in values of x and y and solve for c. Do not forget to plug that c value into your antiderivative to give me your final answer. All right, guys, have a wonderful day. I'll talk to you soon. Bye.